Number 11, we are told to remove the capacitor from the circuit in the figure and set R equal to 238 ohms, L is equal to 277 millihenries, and the frequency is 60 hertz. Our alternating EMF is 36.0 volts as well. We're asked to find Z for A. This is similar to a previous problem, number 10, where we're given this figure. The only difference is in our number 11, we remove the capacitor from the circuit, so we're not given a C, whereas in problem 10, we were given C. It's important to write down all of our values so we know how to solve this problem. First, we have our resistance, which is going to be 238 ohms. We then have our L, which is inductance, which is going to be 277 millihenries. We then have our frequency, which is just going to be 60 hertz. Lastly, we have our alternating EMF, which is 36 volts. To solve for Z, we can use a formula which we previously used, and that is that Z is equal to the square root of R squared plus XL, which stands for inductance, minus X of C, which stands for the capacitor, squared. And got that from previous problem 10. We also need these two formulas below it, this X of L and this X of C, because typically we're not given X of L and X of C. We have to break it out and solve for this. If we come back down to our problem, we see that we have all of the values that we need to solve here. For our problem, we are told that the capacitor is removed. So since the capacitor is removed, we can rewrite our Z without our X of C in it. So for our particular case, here it's going to be Z is equal to the square root of R squared plus XL inductance, since we have our L, squared. It's really going to be minus 0 squared though, because we have removed a capacitor. So we have a 0 capacitor. So we do not need to solve for our X of C. We do need to solve for our X of L though. To do this, we have our inductance, which is 277 millihenries. We have to multiply this by a -3 just to put it in henries, and multiply this by 2 pi times the frequency, which here is 60 hertz. The answer we're going to get for this is that our X of L is equal to approximately 104 ohms. Now we can plug this back into our equation right here and solve for Z. We can say that our Z is going to be equal to the square root of our R squared, which is 238 ohms squared, plus our X of L, which is 104 ohms squared. And both of those are going to be in the same square root. And we are going to get approximately Z is equal to 260 ohms. That's the answer for part A. For part B, we're asked to find the phase shift. We were asked to find the phase shift in part 10 as well, and we have done something similar where we use the equation tangent phase shift is equal to X of L minus X of C over R. If we go down to 10, we can copy this, because this is the equation that we need to use. And from here, we can just plug in our values. Since we don't have a capacitor, this is just going to be phase shift is equal to arctangent X of L over our R. And our X of L is 104 ohms from here. And our R is 238 ohms. We have to make sure that our calculator is in degrees, because that's what we solve for phase shift. That's how we find phase shift. And we're going to do arctangent of 104 divided by 238, and that is going to leave us with the phase shift of approximately 24 degrees. For question C, we are asked to find I, which is the current or amplitude. And for this, we in number 10 did something similar. We were asked to find the current, and we basically are just going to use I is equal to the alternating EMF divided by Z. This is equivalent to I equaling V for voltage over R resistance. So if we go to our alternating EMF, we can see that it is written in voltage, and that our Z is written in ohms, which is the same, or which is similar for resistance. So if we write this all out, we're going to get I is equal to our alternating EMF, which is 36 volts over our Z, which is 260 ohms. And that means that our current, and that's the answer for part C.